Okay, so the other day we focused more on the series circuits. Now we are looking more at the parallel circuits. Okay. So just to kind of refresh again, it says parallel circuits. They have more than one path that the current can flow. Paths can also be called branches. Okay, the current divides between the branches. Not all current goes into each branch. Okay, so just like I used the analogy of toll booth the other day. In this case, this is how our toll booths are lined up. Everybody goes into a separate branch or separate lane. Allows for the flow to be a little bit easier. Okay, allows for the current, in this case, the current to flow faster the more branches there are. Since there are multiple paths the current can take, if one device breaks, devices in the other branches will still work. Okay, so we said the other day with a series, thinking about Christmas lights, if one light goes out, all of the lights go out. In a parallel situation, that would not be the case. Okay, so you can think about your house. If one light bulb goes out in your house, do all the light bulbs go out? The answer is no. Okay, and that's because your house is wired in parallel. Okay, so each light bulb or each outlet or each device that you have, refrigerator, toaster, whatever, they're all on a different branch of a parallel circuit. Okay, and these can have multiple branches. Okay, and if one goes out, one breaks, the light bulb goes out, it's not going to affect the other ones. Now looking at current, okay, current is divided among the paths. So current can be different for each device. Okay, it depends on the resistance of that device. Okay, if it's greater resistance, that means the current's going to be less across that device, so on and so forth. Okay, the total current for all the circuit is equal to the sum of all the branch currents. So as we add branches, okay, the currents will continue to add up to each other, and it will get higher and higher and higher. So, in your kitchen, when let's say all your outlets are on one parallel circuit, which there might be multiple circuits in one room, but let's just say all your outlets are on one circuit, and you have your toaster going, you've got your microwave going, you've got your refrigerator going, you've got your blender going, all these things going at one time. Now the current in that wire, in that circuit, is going to continue to increase, increase, and increase. And at some point, it might get too high, and that's when your circuit breaker will pop. Okay, that's to save your wiring system from overheating and melting, and possibly causing a fire. So it's a safety device that's going to keep that from happening. But yeah, so the more you add in, the higher that current is going to get. So we add up all the currents. This would be the current in each of the branches. So if there's two branches, it's just going to be those two. If there's a third branch, it would be those. It would be three added together, so on and so on. Okay. You can solve for the current in a device using the resistance for the device and the voltage from the battery. So we'll take voltage equals current times resistance. Okay. Now, voltage is the same at all points in the circuit. Now, this is important, and this is mostly why our house is wired in parallel. Because now, if everything is parallel to each other, that will allow the voltage to be the same. And each device that we have in the United States that we plug into an outlet is all designed for 120 volts. So no matter what person is, or what device we're using, each of the devices are designed for 120 volts. So we plug it in and it works properly. If that voltage changed, like it does in a series circuit across each device, then our devices wouldn't work properly. Okay, so every device has a voltage drop equal to the total voltage from the battery or the outlet. Okay, so if we're using a 9-volt battery, that means that every branch that's connected to that 9-volt battery will have a 9-volt voltage drop. Okay, so it will drop from that full amount across that branch. The resistance says the more branches, the less overall resistance. Okay, because just like the toll booth, if you had multiple choices of toll booths to go into, okay, now it will allow the flow of the vehicles to travel easier. Okay, same thing here. When you have branches of your parallel circuit, the current can flow easier because it's got more choices to go in. Okay, so some will go one path, some will go another path, so on and so on. And the more branches you have, the less resistance it will be because the current has more choices to make. So the overall resistance will decrease the more branches there are. So resistance decreases as more branches are added. To find the total resistance, use the battery voltage and total current. So calculate the current for each device and total current for the circuit, and then we will find the total resistance of the circuit. So we're dealing with a parallel circuit. So each of the branches in a parallel circuit have the same amount of voltage going through. Whatever the total voltage is, that's the voltage that's going through each of the resistors. So in this case, the total voltage is 240 volts. So we're going to set up to find the current in each device. We've got to set up just like we have been. We're going to say V. Oops. Let me get my pen. There we go. Okay. So we're going to say that V equals I times R. Now, for each of these, since it's a parallel circuit, okay, in a parallel circuit, the voltage that we're going to use is the total voltage, okay, VT. And we're looking for the current that's going through the first branch, and we're going to use R1. Okay, you can see R listed here as R1. Okay, so if we can say that 240 equals I1 times 120. So it's I times 120, so we're going to divide both sides by 120. Divide this side by 120. Cancels the 120 out there, so we get 240 divided by 120. So I1 is equal to 2 amps. Okay, and we've got to do the same thing for each of them. Okay, so we got VT equals I2 times R2. So again, we've got 240 equals I2 times 45. So we divide both sides by 45. $240 divided by 45, so we get I2 is equal to 5.33 and so on, okay, amps. Now we're going to look at the last one on here. VT equals now R3. Oh, sorry, I meant I3. Doesn't really matter what order we put it in, but I just want to, for consistency's sake, I want to make sure that I put it in the right same order. So we got I3 times R3. Okay. So we got 240 equals I3 times R3, which is 360. Okay. So now we divide both sides by 360. We take 240 divided by 360, and our I3 is going to be equal to 0.667 amps. Okay, this is going to continue 0.6666666 so on, just like this is 5.333333. So to get our total current, we have to add these up together. We're going to notice it's going to come a little shy of what the actual answer is because of that rounding situation. Okay, I'm just going to move to the next screen so we can look for that. Okay, so to find the total current first, okay, we know that I total is going to be equal to I1 plus I2 plus I3. So in this case, it was 2 amps plus 5.33 amps plus our last one, which was 0.667. Okay. When you add that up, you get an I total of equaling 7.997 or something like that. Okay. This is the only reason why it's not 8 on the dot is just because of these rounding issues. So we can round that up to 8 amps. Okay, so that is the total current. Okay, so now to find the total resistance. Okay, if you notice, the first resistor was 120, then we had 45, and then we had 360. And we learned that as we add more resistors, the total current actually would continue to go up. Okay, and the total resistance would actually go down. Okay. Because the voltage stays the same. Anytime the current goes up, the resistor resistance must be going down. Okay, so if we look here, using the same formula again, we're going to use our total voltage. Okay, is equal to our total current. Now we're looking for our total resistance. Okay, so if we plug these in, we got 240. Equals our total current, which was 8, okay, times our total. So to solve for our total, we're going to divide both sides by 8. So we get an R total equals 240 divided by 8, which is 30 ohms. Okay. Notice the total resistance in this case is smaller than each one of these individually. Okay, and if we were to add up another one, it would be even smaller than that. And the resistors would get even smaller and smaller and smaller, the resistance would, until the current gets so high that if this was a house, the circuit breaker would pop.